Hi everyone. In this video we're going to talk about the binomial model, but first we're going to discuss Bernoulli trials. A Bernoulli trial is one in which there are only two possible outcomes, either success or failure. We denote the probability of success with a P, and then we denote the probability of failure with a Q. But success and failure are complements, so we can always find Q by taking 1 minus P. For Bernoulli trials, they are also independent, so the probability of success and failure remain the same for all of the trials. So an example of this is rolling a die. So we'll go back to rolling a die and observing a 6. So the success will be seeing a 6, and failure will be seeing some other number other than 6, which means that our probability of success will be 1 out of 6, and our probability of failure will be 5 out of 6. The first question says, what is the probability that the first roll is a 6? Well, it's just the probability of success, which is 1 out of 6. The next question says, what is the probability that the third roll is a 6? Be careful of the questioning here. It's not saying anything about the first or the second roll. We have no idea if those were successes or failures. It's just asking for the probability of the third roll. But for Bernoulli trials, the probability of success remains the same for all of the trials. So the probability of observing a 6 in the third roll is the same as the probability of observing a 6 in the first roll. It's just 1 out of 6. But in the next question, it does talk about the first and the second trials. It says, what is the probability that the first 6 you observe is on the third roll? So it's implying that you have 2 failures in the first and the second trial, and that the third trial is a success. So we're finding the probability that we have a failure, and then a failure, and then a success. And when you are using an AND with independent trials, we multiply those probabilities together. So we have the failure, which is 5, 6, times the failure, which is 5, 6, times the success, which is 1, 6. And we get this as an answer. The next question is different. It says, if we roll a die 3 times, what's the probability that we see exactly 1, 6? Notice that in this case, we have no idea when we're going to see that 6. Is it on the first roll, the second roll, or the third roll? We don't know, so we have to include all of those calculations. So our possibilities here are that we observe the 6 on the first roll and not the second and third. So that's here. So we have a success, a failure, and a failure. Or we have a failure, a success, and then a failure. Or we have 2 failures and then a success. Those are the 3 ways that we can see exactly 1, 6. And we do those calculations, we get these, but we can multiply in any order. So we're considering the order here, but the key is to notice that these are all the same numbers and that we have 3 of them to give us our final answer here. This is an example of where we would use a binomial model because we are looking for the number of successes in a Bernoulli trial, but we don't know where that success occurs, so we include all of the possibilities. So a binomial distribution represents the number of successes and failures in n independent Bernoulli trials. The notation is this. We use a capital B. N is the number of trials, and P is the probability for success. And then capital X represents the number of successes that occur. We have some conditions for this. We need a fixed number of trials that are conducted. So for example, in our last example, we had 3 rolls. So 3 trials were the fixed number of trials. There are only 2 possible outcomes for each trial. So again, in our last example, we were either observing a 6 or not a 6. The probability of success is the same for each trial. So we see that as long as we have independent trials. And so in our last role, we were looking to find the probability of observing exactly 1/6, where we had a fixed number of trials and the probability of success and failure were the same for each trial. We can use this formula, and I'm not even going to explain the formula because I don't want you to use it. We're going to use calculator commands. We have 2 calculator commands that we're going to use, either binomial PDF or binomial CDF. We use the PDF command when we're wanting to find exactly a certain number of successes, and we use the CDF command when we want to find a range of successes. So again, the binomial PDF command means that we're going to find the probability of observing exactly that amount of successes in a certain number of Bernoulli trials. And the syntax for the command is here. So we use binomial PDF, and then we put in the number of trials, the probability of success, and then how many successes we want to see. And I have an example of that because I'm going to use our previous example. So again, we're looking for the probability of observing 1/6 if we roll the die 3 times. So then the n is 3, the probability of success is 1/6, and we're looking for 1 success out of those 3. So you're going to find the binomial PDF command under this distribution button right here. So we're going to hit second vars to get to distribution, and then we're going to have to scroll down pretty far to find the binomial PDF command. So this is the same place that we went for the normal CDF command. So you'll see here we go to second vars and then scroll way down. And I'm going to scroll down even further so that you can see both commands here. So there's binomial PDF and binomial CDF. For this example, we're going to use PDF. We had 3 trials. The probability of success is 1/6. And we are looking for 1 success. We paste it and then hit enter again. And we have our answer. And this is the same answer that we got on the previous page. We use the binomial CDF command when we want to find the probability of observing less than or equal to a specific amount of x's. So this is a range, but it works specifically with less than or equal to. And then we use the same NPX in the syntax. So again, N being the number of trials, P being the probability for success, and in this case, X being the number of successes or less than that number. All right, let's do an example. So we have an Olympic archer can hit a moving target 100 yards away 82% of the time. Suppose the person takes 9 shots at the target. So we have a limited number of trials. We have 9 trials. We have only 2 possibilities. They either hit the target or they don't. We have the probability of hitting the target is 82%, which means that the probability of missing the target is going to be 18%, 1 minus that. So that means that we have our binomial distribution, and we can use those calculator commands to answer the following questions. What's the probability that there are exactly 5 hits? So because we're looking for an exact number of successes, we're going to use the binomial PDF command. So in order to explain kind of what happens further with a binomial CDF command, because it gets a little more complicated, I just wanted to give a visual of what we're finding in terms of probabilities. So for this archer, we have a discrete number of possibilities of happening, right? They don't hit the target. They hit the target 0 times, 1 time, 2 times, 3 times, 4 times, 5 times, 6 times, 7 times, 8 times, or all 9 times. We're looking for the probability of hitting exactly 5, so we're going to use the PDF command, where n is our number of trials, 9. So we're taking 9 tries at hitting this target. The probability of hitting the target, the probability of success, is 0.82, and we want to know the probability of getting exactly 5 targets. And we get our answer here. For the next part, it says, what's the probability that there are at most 5 hits? Well, at most means 0 or 1 or 2 or 3 or 4 or 5, but 5 is the most. So we're looking at this range. Whenever we're looking for a number of successes or less than that number, we use the binomial CDF command. So I'm literally entering the same values here, but I'm using the CDF instead of PDF, because that CDF command basically adds up all of the individual PDF commands. And we get this 0.0615. The term at most 5, there are other ways that we can say this. So we could also say 5 or less. That would give us the exact same scenario. Or we could say no more than 5. So again, no more than means not more than 5. So 5 or less. So these 3 terms give us the exact same scenario of this 0, 1, 2, 3, 4, or 5. And so for all of those, we're going to just use the binomial CDF command straight with the number of trials, the probability of success, and that 5. It gets a little bit trickier when we have different wording. So notice that the next one, it says, what is the probability that there are less than 5? Less than 5 does not include 5. And because this is discrete, this specifically means 4, 3, 2, 1, or 0. So that is less than 5. We're still going to use the binomial CDF command because it uses the value and less than that, but we're not going to use 5. We're going to use 4 because the CDF command includes this number. So this says 4 or less, which is the same as saying less than 5. The next one says, what is the probability that there are more than 5 hits? So now we're looking at more than 5, which is 6, 7, 8, 9, 6, 7, 8, or 9. The CDF command only works for the value and less than that value. So now we need to use the idea of complements. If we want to find the probability of this upper range, we want to take 1 minus the probability of this lower range. And again, the CDF command will find the probability of that lower range. So to find the probability that there are more than 5, we're going to take 1 minus this binomial CDF using 5, because we're going to take 1 minus this range to get this range. If you need me to explain that one again, let me know, because this is probably where I see the most mistakes, is people forget to use that complement rule. Same problem, we just have some more questions here. So same Olympic archer, 82% of the time they can hit the target, and we're taking 9 shots. What is the probability that there are at least 5 hits? Well, at least 5 means 5 or more. So this would include 5, 6, 7, 8, and 9. Now we're going to use the complement rule again. Because that binomial CDF command only works with a value or less than that, so we're going to take 1 minus this range to get this upper range. But this range is 4 or less. So we're going to do 1 minus the binomial CDF command using 4, since we want to subtract off the 4 or less. Other ways of saying at least 5, we could say 5 or more, or we could say no less than 5. These wordings will give us the exact same scenario as this one, and we would use the exact same command. The next example asks us to find the probability that there are between 5 and 8, and this is inclusive, meaning that we're including the 5 and the 8. Again, we're going to use the, so here's our scenario, right? We want to be between 5 and 8 and include the 5 and 8. So what we want to do is if we take this CDF command using all the way to 8, if we take and find that value and then subtract off the 0, 1, 2, 3, and 4, we'll be left with the 5, 6, 7, and 8. So we're going to use the binomial CDF command for 8 and then subtract off the binomial CDF command for 4 because we want to include 5 in our answer, so we don't want to subtract it off. So again, this will be the same binomial CDF, but we're going to use 8 minus the CDF with 4. When you put this in your calculator, and I know I'm not showing the calculator here, but when you do this, you can do it all at once. You do the binomial CDF command with 8, you get it into your calculator, hit minus, do it again with 4, and then hit enter. So this is all one line in your calculator. You don't have to find separate values and then subtract. And then finally, what is the probability that there is at least 1 hit? So at least 1 means 1 or more. Oh, I don't have a picture for this. So remember that if it's 1 or more, so if I have I'm looking at this range here, 1 or more, at least 1, the complement of this is 0. So if I do 1 minus the probability of getting no hits, well, I'm getting exactly no hits, so I'm going to go back to, the PDF command for 0. And actually, here's where it doesn't really matter which command you use. You would actually get the same answer if you use the PDF or the CDF command for 0, since there's nothing less than 0 anyway. But remember that you're doing 1 minus this. Also notice my answer. I got a whole bunch of 9s, but I did not round this to 1. If you round a probability to 1, you are saying that they are guaranteed to get at least 1 hit, right? A probability of 1 means that that event, that idea, that thing that's happening will always happen. That's not the case here. Now, the probability that it doesn't happen is extremely small, but it's not a guarantee. So don't round this to 1, right? We're talking about probabilities here, so you do not want to say that there is an absolute probability that they will get at least 1 hit. When we use the binomial distribution, we also want to talk about the mean and the standard deviation, but please don't get this mixed up with how we calculated the mean and the standard deviation when we were talking about tables in the last video. In that last video, we did expected value and standard deviation, and we're using the one variable stats command. That's not what we're doing here. For the binomial distribution, the formulas for finding the mean and the standard deviation are very easy. The mean is just the number of trials times the probability of success, which makes sense. If I say I'm rolling a die, I'm rolling a die 3 times, what's the probability that I'm going to get a 6? Well, on average, 3 times 1 6 is going to give you the average of those probabilities. The standard deviation is the square root of the number of trials times the probability of success times the probability of failure. And remember that Q is 1 minus P. So using this same scenario with the Olympic archer, if we want to find the mean, we're going to take the mean, which is mu, because we're talking about a model, the number of trials times the probability of success, and we get 7.38. This is a mean, so it doesn't have to be something that's going to actually happen, right? It's similar to the idea when we were talking about expected value. Of course, it's not possible for her to hit 7.38 targets, right? She's either going to hit 7 targets or 8 targets, but not somewhere in between that. But this is a mean, meaning that we're, if she's doing this same thing over and over and over again, what is the average of that? So don't round this. Do not round this to 7. It should stay at 7.38. The standard deviation is, again, the square root of the number of trials times the probability of success times the probability of failure. And so we just take the square root of the multiplication and we get 1.15. Make sure that you have these formulas written down, because this is where we're not going to use our calculator to make these calculations. We're going to use the formulas. So here are the formulas up here. Okay, one more example here. It says the probability that a new car of a certain model will require repairs during the warranty period is 0.15. A particular dealership sells 85 such cars. Let X be the number that will require repairs during the warranty period. So we have a certain number of trials, so a limited number of trials, 85 trials, so 85 cars. The probability of success, which I know sounds weird because this is the probability that it's going to require a repair, which I know that doesn't sound successful, but in our mathematical sense, this is our definition of success. So the probability that it needs a repair is 0.15, and you only have 2 possible outcomes here. Either the car will need a repair within the warranty period, or it won't. So we have a binomial distribution with n equaling 85, our probability of success equaling 0.15, and our probability of failure is 0.85. So what is the probability that there are exactly 20 cars that need repairs? Exactly a certain number of successes means that we're using the PDF command, the binomial PDF command. So we would use binomial PDF with our number of trials, probability of success, and the number of times we would see that success. What is the probability that there are less than 7 cars that need repairs? Less than 7 means that we're not including 7, right? That's 0, 1, 2, 3, 4, 5, 6. So we're going to use the binomial CDF command with 6, since we don't want to include 7 in our answer. So we're using the CDF command, Again, number of trials is 85, probability of success is 0.15, and we want 6 or fewer. What is the probability that there are more than 10 cars that need repairs? Well, more than 10 would be 11, 12, 13, 14, all the way up to 85. So we're going to need to use the complement rule with 10 or fewer. So we're going to use 1 minus the CDF command using 10, since we don't want 10 as part of our answer because we want more than 10 in our answer, which means we want to subtract off the 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. And then finally, the mean and the standard deviation. Remember that the mean is n times p, so 85 times 0.15, and don't round that. And then standard deviation, which is the square root of npq, where q is the probability of failure. All right, if you have any other questions on binomial model, please let me know.